All right, so then welcome back everyone to TEWA 1, the advanced data analysis. So today it will be the last lecture before the holidays. So before we move on to the optimization part, let's just try to have a quick recap to think about what we have discussed the last week. So the last week we spent a lot of time discussing something called a hierarchical model. We discussed the hierarchical model both on the conceptual lecture by me and also the practical lecture on data camp. So the hierarchical model in essence, basically as the name suggests, there is a hierarchical structure. So what's this structure? What does it look like? This structure assumes that on top of all of the individuals, in this case, many participants, on top of that, there is a common population structure behind it. So assuming that all of the participants, they are sampled from the same population. So then you could imagine there are two levels. One is the individual level, each different participants, and another level is the population level, the underlying population where we assume the individuals are drawn from. Okay, so two levels. So because there are two levels or two hierarchies, we could have multiple names to describe the same thing. So one is a hierarchical model, as it clearly indicated. The other one can be a multi-level model. And then the third one is, if you remember, we mentioned two concepts. So if you could imagine here, if we have the two levels, one is the group level or population level, the other one is the individual level. What you can imply one step ahead, which will be that the group level or the population level, it describes something in common, right? Even though there are different individuals, they are sampled, they are assumed to be sampled from the same the shared common population. So this is something they are in same. At the individual level, then there will be something different. Each person is a little bit different from the other one, and so on and so forth. And to describe these things, so we could say this is commonality and this is individual difference, right? And then the commonality can be described as something called a fixed effect, because this is the same for everyone, so this fixed. And here this individual difference, because everyone is randomly sampled from the distribution, from the entire population. We have really not much idea to precisely describe how each person is, but we can roughly estimate how random they are according to this population. So to describe this effect, we call it a random effect, okay? So fixed effect and a random effect. If we want to combine the two effects together, how they are called, we can call them combined effect, but this is not really common in the literature. In the literature, this is often termed as a mixed effect, okay? So mixed effect. So far, I quickly summarize the three terms that you have heard about from me, from whatever paper, literature, to describe the same thing. So the hierarchical structure can be called by three names or three terms. First, hierarchical model. Second, multi-level model. Third, mixed effect model. Same thing, okay? So we talked about, even though they have different names, but the shared, the underlying structure is always like this: group level, individual level. And this visually can also be interpreted, also visually, the same structure can also be represented a little bit differently. So we could say, well, using an equation to describe how the hierarchical model works. If you remember the idea, whenever we have a long kind of conditional probability equation, where to look at first. So we always look at the rightmost. Here, this is the prior of the group level. So that means this. And according to the group, then this is the individual level. Then that's this, okay? And then according to the individual level parameters, we have this PD thing. So those are like this part. This is the likelihood. So if we always look at from the right-hand side to the left, so everything is much more easier to understand. Not so easy, but it's easier than if we look at from here to here. Doesn't make too much sense in my opinion. Okay, and also visually, we usually describe the hierarchical structure as a normal distribution because this is commonly seen like normally distributed. So we assume a underlying normal distribution. This is a group level, and here they are the individual level. Here the same thing, just a little bit differently illustrated. And very lastly, this is the full version. So because we are doing Bayesian statistics, everything has to have a prior distribution. So here, this part, you could imagine it is the same as this one, right? There is a group level normal and then some individual level normal distribution. Yes, okay, here group level normal distribution, individual level normal distribution, very, very well. What is additional is here the top two distributions. Because we know that for a normal distribution, there are two parameters. One is the mean of the normal distribution. So we are focusing on this one. So one is the mean of the distribution. The other one is the standard deviation of that distribution. Because, as I said, we are doing Bayesian, we need priors for both of the parameters. So that means what? That means we need to specify a prior distribution for the mu parameter. We also have to specify a prior distribution for the sigma parameter. Okay, so this is how we ended up the last time. And we tried to code up the direct translation from equation to the Stan code using our simple Ritzler-Wagner model. But we encountered a problem when we were trying to do that, if you remember. So normal distribution, as we know, there is no limit, okay? So here is infinity negative, here is infinity positive. This is okay if we have a regression model, because regression model, the parameter can be anything, can be positive, can be negative, can be zero, can be large, can be small. So no limit. In our case, on the other hand, we have something slightly different. So if you recall the equation, we have V on the next trial, right, equals V on the current trial plus the learning rate, and then times the R minus the VT, okay? This is the reward prediction error, and then this is the learning rate. And then we use the learning rate multiply with the prediction error to update the value calculation using the task. And by definition, this learning rate parameter alpha, it is something like between 0 and 1, okay? This is by definition, it has to be like this. So in other words, that means there is a limit of the learning rate. There is a lower limit, 0, there's an upper limit, 1, which contradicts the idea that the normal distribution doesn't have a range. So you see the conflict, I guess? And what we do as a workaround to solve this challenge is that, well, we do have a normal distribution, but we also have a limit, okay? 0 and 1, 0, 1, okay, good. So we only take the density. Remember here, this is the density function, this is the area under the curve. So we only take the density in between the range so that we don't take the parameter smaller than 0 and the larger than 1, we don't take it. Okay, good. Sounds plausible to solve this problem, but in practice or in reality, this is really troublesome in the sense that we have the MC robots, if you remember, and then the MC robot, it travels everywhere, right? If we say, well, there's a closed door here, that the robot cannot travel beyond it. So what you can imagine is that the robot will hit the door, right? There's a wall in front of you. You're trying to go beyond it, but then you cannot do it because it's not possible. So what you do is that you hit it. You hit against the wall. If the robot would imagine something is interesting behind the wall, so it's trying to push against the wall, even though it can't go there. But the tension to push against the wall is quite annoying, right? So we do not want to limit the freedom of the MC robot. So this is like the rough essence of it, okay? To simply put, we could imagine that anything that we arbitrarily, so any cutoff that we arbitrarily impose on a distribution where it doesn't have a limit, this will cause a lot of problem. Okay, this is the question or the challenge that we want to solve. Okay, good.
Sorry.
And now that, yes?
I want to ask a
Go ahead.
question. I don't know when is the right time for that.
Yeah, sure, you can, go ahead.
So when we generate this hyperparameter distribution, we use two parameter distributions for mu and for sigma. And so that's like, so from the two distribution on the top, we generate the hyperparameter, the group parameter distribution. And what I'm not sure about is how do we get these individual distributions, because then it's only one distribution anymore on the group level, but to get the distribution again on the individual level, we also need two parameters, right? Mu and sigma. And yeah, so that's just something I'm still confused about where the second parameter comes from for the individuals.
Do you mean like this, where to get this?
Yeah.
Yeah, okay. So because, well, yeah, okay. So if you remember the coin example or the globe tossing example, so we have like 6 water out of 9, right? And then we toss it, and then we use a binomial, and then the theta parameter in the end, what we get is something like this, right? This is the posterior for that.
Yeah.
Even though this distribution, you could imagine there is a mean and then there is a scale parameter, even though it's not symmetrical, it's all right, that doesn't matter. But this is the posterior distribution only to describe the theta. So this is the distribution only to describe one parameter, not two.
Right.
So if what you are saying is that we care about both the individual level mu, let's say mu1, and individual level sigma and sigma 1, something like this, sigma 1 and mu1. If we care about that, then at the individual level, we will not have one parameter, we will have two. One for the mu, the other one for the sigma. So for both of the mu and for the sigma, we will have a distribution for that. But this distribution is the posterior sample. This has nothing to do with the individual level sigma.
Right, so we get the distribution just because we sample enough from the group parameter distribution
and then
to get another distribution.
Exactly. If we do point estimation, like more classic methods, like maximum likelihood estimation, we will only get this number, one line, one number, one point estimation. Right. We will not get the entire distribution. So this distribution is something we get by default if we are using MCMC.
All right.
It's a given, let's say, it's a given, yeah.
Just to recap, so basically this group level distribution we can get analytically from having a mu and having a sigma, and then the individual level distributions we get numerically or basically statistically by sampling.
Everything's by sampling actually, because here this tool, we also sample it by using MCMC. Yeah.
Okay.
Yeah. I think to keep that a little bit more explicit, this parameter, we could imagine that this is only the individual level mean, and there is not an individual level standard deviation from here. It's not there.
Okay.
Yeah.
Okay, thank you.
Sure. It can be a little bit more interesting, honestly. So if you don't mind. So let's say this is a group level distribution for whatever, the entire population, many people, younger, older, and healthy, and patients, everything's there. We assume there is one in overall distribution. And we, of course, have the prior for the mu, for the sigma, okay? The prior for that. And now we say, this is too much, too little. Let's say this is too little because there might be some subgroups underlying this common group. And we say, okay, maybe this is healthy control. And then this is something like patients, whatever patients. And we say, okay, here we have at the subgroup level, there's also a subgroup distribution, one for the healthy control and the other one for the patients. We could imagine that these two distributions, they follow this one. But they also they might also have their own sigma. So this mean somewhere around it is sampled from the top one, but they might have their own standard deviation. Maybe the healthy control is narrower, and maybe for the patient is a bit wider, because for patients, the heterogeneity is usually a observation, right? They are less common among each other, relative to each other. And then at the level below, so we have then the one that we are familiar with, the individual level, healthy participants individual level. And here, these are the patients individual level, individual patients. Is it better, or does it make you feel more confused?
No, it's all right. So I'm just
Okay.
wondering, for example, if we say the healthy control and the patients, they have different moods, different means, because we sampled from the distribution above. But also the sigma is different. Doesn't this then mean that we need to sample the sigma from two different distributions to basically make sure that they do have different distributions, or that they do have different standard deviations?
Yeah. So the question is about if they are, if these two, they have their own priors, right? This is question.
Yes.
Yeah. So for the prior distribution, from a practical perspective, I will use the same prior distribution, but independent. Not really the same, but two, they're identical. And then we collect data, and we say, after observing the data, given the data, if the posterior of these two, they say is different, then it's different. So so let's say it this way, at the beginning, I don't say anything, you are the same or not. But given the data, given the evidence that I collect, and then evidence is suggesting that, okay, even though I pre-assume you are the same, that two things are identical, but after incorporating some pieces of new evidence, one might be larger, the other one might be lower. Rather than at the beginning, a priori, I already assume these two are different. And then I use incoming evidence to confirm me or maybe disconfirm me. So these are two different approaches. Do you see what I mean? Yeah. Okay. Good. Then I guess I will proceed. Yeah, good. So we have this thing, normal distribution who doesn't have a limit, but we want our parameters to have a limit by definition. So we want to solve the problem. To solve this kind of problem, we will try to optimize our STAN script, our STAN model. So I introduced already three of the approaches. I will quickly go through them. So the first one is to pre-process the data, to do as much as you can in terms of data preparation outside STAN, do it in R. When everything's prepared, ready, and you give it from R to STAN, so STAN only do the sampling. And the second one is to specify a proper model. This is a little bit tricky when I was mentioning about this. Tricky in the sense that if you design experiments, but you have never heard about this experiment, it's suitable for whatever kind of modeling. So how you can know there's a model you could use to quantify your data? You don't. So usually the best approach is to do project with people who are who has more experience. So if you do a PhD project and then the supervisor knows what experimental design is associated, what kind of model, and then this is easier. And if when you design an experiment, when you were doing the designing part, you have no idea this can be modeled afterwards. But later, through experience, so maybe somebody told you, well, let me maybe give this kind of example. I designed one experiment. I haven't heard about cognitive modeling. I just designed it. I collected data. I have the data already. Good. And then I have a friend who took the TEWA, one of you, for example, Jakob, for example, and he took the TEWA and he has heard about something called cognitive modeling. And I, as a person who hasn't the experience of cognitive model, but I heard a friend who took the course and he knows something, and I just But I just then go to him to say, hey, Jakob, I have the data. Can you try to look at it if this can be modeled? This is quite a typical question that you might ask, right, in research. And then Jakob just comes to me and then he look at my data and he said, yeah, maybe it's possible, but if I could have designed the experiment a little bit more differently, keeping the cognitive model in mind when designing the experiment, everything can be a little bit different, okay? So the scenario is like this, to put it a little bit simply. If you don't know cognitive model when designing experiments, and then you have the data, and then you see something potentially can be modeled, can you do the modeling? Yes, you can. But that is suboptimal relative to when you were designing the experiment. You already know, you already could foresee or anticipate that the data can be modeled afterwards. And then these two scenarios usually will make a huge difference, because if you know the data can be modeled afterwards, you would really design the experiment in a way that it will optimize the model fitting, rather than if you don't know it and then you just did it, and then later on you want to apply model and then it's a little bit suboptimal, okay? This is the scenario. And a real world case of this, how did that happen? If you really have no idea of cognitive model and you just design an experiment and then later on you want to apply a model, what do you do? So even though it is suboptimal, yes, it is, because you didn't know about cognitive model. But as long as you have the opportunity to model it, then just do it. And then the next experiment, what you do is that you will improve your design, keeping in mind that cognitive model is a possibility, and then you might really design the experiments slightly differently so that you can apply model later on more optimally. Okay, so this is how science works, I think, most of the time, because nobody knows anything from the beginning, and then you do it, something fails, something succeeded, good, either way, and then you improve it, you do another experiment, and then to see what else can be observed in addition. And something might succeed again, something might fail again, and then you do a further experiment to find out what is what. So, okay, this is like, I think this is my opinion. So how usually this kind of psychology experiments works, or more in general, just natural science works. Let's say, let's put it this way. I don't know how the other science works. Great. And then the third is about vectorizing. Vectorizing is easier to understand. So the rough indication is if you write down a for loop for 1 to 100, for 1 to 10, for 1 to 200, whatever, as long as you have a for loop, try to find out if this can be vectorized. So vectorized means we do not need to loop if we have a vector. We don't have to loop from the first to the second to the last to do the calculation. So we could use the entire vector to do the calculation, okay? So if we say a plus 1, if a is 1, 2, 3, 4, 5, 6, if you don't do vectorizing, you will do 1 plus 1, 2 plus 1, 3 plus 1, 4 plus 1, okay? And then you get the results. If you do it like this way, the entire vector plus 1, the result will be the same. So it's 1 plus 1, 2 plus 1, 3 plus 1. The result will be the same, but the calculation time, the runtime will be a lot faster, because one way you loop it, each time you only do one calculation, the other time you do it only once. So all those addition, they happen at the same time. So it saves a lot of time. Great. And then lastly, reparameterization, and this will be our final approach to do stand code optimization. So then we will talk about that. This one I'll skip. I mentioned. Yeah, good. Reparameterization. So before we talk about reparameterization, let me explain the term a little bit, because this might not even be an English word, I think, in the beginning. So parameterization or parameterize, this is a word, I'm sure. This means to use parameters to describe something. If you say, I have 2 apples and 3 orange, I want to know how many fruits I have. Okay, so 2 apples and 3 orange. So let's say apple is A and orange is O. If I say I have 2 orange and I have 3 apple, the other way around, 2 apple and 3 orange, and I want to know how many fruits I have. This is parameterized because you are using parameters to describe a problem that you verbally describe. So there's something called a verbal description, verbal, just words, language. And the other one is like mathematical description or parameterized description. So you're translating something from verbal to equation. So this process is just called parameterization. You use parameter to describe something, okay? And in this case, how do I know if I have 5 fruits? Because this is 2a plus 3o, how do I know this is 5? Well, there's assumption. You say, well, either 1 apple or 1 orange, they equals to 1, okay? This is the assumption. This is like in our sense, we have parameters. We say, well, these parameters, instead of unknown, we know it, they equal to 1. So if we know A is 1, O is 1, then 2a plus 3o, it becomes 5, okay? This is parameterization, as simple as that. And then this is something that you can relate, I think. And reparameterization, what that means? Well, re just means do it again, or maybe do it another way. So reparameterization, in a little bit more formal description, basically means to try to find out another quantification to describe the same model. So model is always the model. The model doesn't change. You can use either one equation to describe it, or maybe use another equation to describe it. As long as the model is the same, then it's the same model. But the way to describe it, it might differ from one way to another. So one way might be direct or simple parameterization. The other one is called a little bit more sophisticated parameterization. And we say this a little bit more sophisticated version is a reparameterization of the previous one. Okay, so do it again, just like that, do it again. Do it in a different way, let's say, or paraphrase if you want to link to our daily communication. It's paraphrase something. We describe the same thing, but we use a different word to describe it. So paraphrase and reparameterization, they are the same thing, I think. Good. And let's say we have a quite complicated statistical distribution. And we want to first phrase it, to parameterize it, and then we paraphrase it, we reparameterize it. But the model is always the model. Okay, so here, let me give you a higher level background. So here, when introducing reparameterization, this topic, and then there is always this example, it's called Neil's funnel, because this thing is Neil's funnel, because this distribution is really one excellent example of illustrating the power and the effectiveness or usefulness of doing reparameterization or paraphrase. You will see how that works. And what I will say in front beforehand is this entire Neil's funnel looks a little bit complex, as you can already tell. But it doesn't. I will explain what that means. But even if you think that is quite, even though I think it's a little bit straightforward, it's quite straightforward to understand, but you might still don't get it, don't worry. And you really focus on the concept to see how the paraphrase part is making a difference. This is more important. So to describe something, the something part, the content is not important, but to see the phrase and the paraphrase part, how these two they differ and how the effects they will bring afterwards, what the difference that will be, what the difference will be by using the two different methods. And this is more important, okay? In the end, in our cognitive models, we will never use something like the Neil's funnel, but we will use the approach of paraphrase. We could borrow from this example to our example. This is more important, to transfer the knowledge from one which is seemingly complex and meaningless to something that we are interested in. Good. Okay, the Neil's funnel. So how to understand this part? So there is a multiplication sign. So that means something is multiplied with something else. Okay, good. First one is a normal distribution. Can you see that? The first one is simply a normal distribution, y03. This is equivalent to, well, I have a y, it is sampled from normal 03. Okay, then we know it. Good. And what is this? This is also a normal. There's x, there's a 0, there's exponential y/2. Well, what that is? This is x, and x also follows normal distribution with a mean of 0, good, and with e to the power of y/2. Okay, yeah. Also not so bad. We know normal distribution, one is the mean, the other one is the standard deviation. But in this case, this standard deviation depends on here, this y. Well, even though there is a dependence, but it's nothing else than a normal distribution. It's just a normal distribution. Good. Next, we see something a little bit different. So we have xn here. So we have xn, good. And in this case, we have 9 of the axis. We have x from 1, 1, x2, until x9. There are 9 of them in total. And each of these 9 x variables, they follow this normal distribution. Okay? And that's it. That's it. To implement this model in the Stan language is surprisingly straightforward, just as the way I described. So if you see, let's look at here. If you look at here first, this is to implement this part. And then if you look at here, this is to implement this part. And then there are 9 of x instance. So x1, x2, x3, 2, 3, 4, 5, until 9. To implement this model, this is extremely straightforward, honestly. Okay, that's it. So what is the difficult part? Why this is the excellent example to demonstrate parameterization or reparameterization? It is because if you are interested in the shape of this joint distribution, so here we have in total 9 variables plus 1, okay? 9 of x, and then 1 is y. So in total, we have 10 parameters. If we have multiple parameters, how can we describe the distribution? We have joint distribution and conditional distribution. And in this case, the joint distribution is quantified by 10 variables. Remember what is the joint distribution? If we have 2 variables, let's say we have 1 of x, 1 of y. If it's something like this, oops, this mouse is really annoying. If we have something like this, yeah, this is like density. So here the density is very high, and then the density is lower. The density is the lowest at the very edge of the surface. So this is the joint space of x and y. When we have only 1 x and 1 y. In the current example, we have a little bit complex case where we have 1 y but 9 x's. So then the joint space will be a 10-dimensional space. 10-dimensional space is difficult to illustrate, to visualize. What we do is we take one of the x and y to see how they look like. So then this will become a marginal distribution, irrespective of the other 8 of x, and only look at 1x and y, okay? So this is the graph. So here is only 1 dimension of x and y. So this will be something like this, conceptually the same. We are looking at the 2-dimensional reduction of how they look like, how the density looks like. Okay, good, enough detail. If what I said from the last 10 minutes doesn't make any sense to you, don't worry. Now from here, this is more important. What is important? So here, this is the shape. So here, this graph, this is the shape of the joint density. What you can tell is here there's a very thin tail. And what we have here is something like large but scarce. Okay, if you look at density, this is very scarce. This is the observation. The shape is different between the two parts. Okay, here is narrow and dense. Here is scarce but large. Okay, this is the geometrical property of the distribution. This is the observation we can tell. Good, good. So far so good. And back to this, like the MC robots algorithm. So what we want to have, remember the goal is always to find out the density, where is high, where is low, using the MC robot. And tell me where is high, where is low. So the density here, the density is high, good. And somewhere here, the density is low, okay? And then the MC, it is trying to find the property. And also recall that the MC takes steps. It could go from here to here. It could go from here to here. So in one example, it takes larger step. In another example, it takes smaller step. Okay, it takes steps. So how far you go by one step. So now you will see the trouble or the challenge. So if you have a appropriate step here, so what is the step size that you need to really travel this space? So it's very tiny, it's very dense. So how would you imagine the step size? It will be very tiny, right? If you go very large, then if you go from here to here, well, you will skip all the information. You don't want that. So what you want is you take very tiny steps so you can have a fine graded traveling experience along this part. Good, makes sense, I guess. And now if you are using a really small step here, which works perfectly, but if you move up, like from here, let's say, if you move across this boundary, let's call it boundary or neighbor, let's move from the lower part to the upper part, this small step is too small, right? This is also a scarce space. Remember that there's not too much information. If you take a tiny small piece of step, it will take an infinite amount of time to explore all the information there. It takes too much. So conversely, for the upper end, maybe a larger step will be better. Okay, from here to here, and then here to here, and here to here, and here to here, something like that. So a larger step size will be better for the upper part. So now you see the trouble. For the lower part, let's sit here. For the lower part, a tiny step size will be better, really tiny. But for the upper part, like a larger step size will be better, okay? If you do the larger step size from the above and then travel to down below, really you will skip too many information. It doesn't work. Okay, good. So this is the challenge. There is not a one size fit all step size for the MC algorithm to sample this really weird looking statistical distribution. Okay, that's the challenge. Good. And how to solve this? How to solve this kind of thing? So usually in the STEM language, there is a recommended optimization approach to solve this problem, which takes advantage of sampling from only simple distributions. So let me repeat. We want to paraphrase something. Maybe some person who is really a native English speaker and he said something or she, and we don't really understand it because the word or the structure of the sentence is too much. I don't understand. I'm a non-native. And then I try to repeat what he or she is saying. And if I do the repeat, I will use simpler phrases. And if the person says something really complex, I don't know what that is. And then I will say, do you mean this and this? In this case, I will use really simpler languages. And then this is a paraphrase, right? So you could imagine, well, for a paraphrasing part, we prefer using simpler languages so that everyone understands instead of using really fancy words. Okay, good. For Stan, it's the same. So Stan also likes simpler languages or simpler phrases, simpler words. So what is simpler for Stan? So the most classic and the simplest distribution for Stan is the unit normal. Unit normal means we have a normal distribution with a mean of 0 and a standard deviation of 1. Unit normal. So it's a unit normal. So this is Stan's favorite term or favorite phrase. And Stan, it will be great that we tell Stan to describe thumb model using the simpler language. So this is our goal. What do we have from the last slide? So we have a normal distribution, right? We have two normal distributions. One is this, the other one is this. This is the normal distribution. And we want to paraphrase the normal distribution using the simpler language, the unit normal. This is unit normal. And then to do it, how to do it? Well, let's say this is the statistical distribution we are interested in. The mean is called mu theta. The standard deviation is called sigma of theta. And here we don't have mu, we have 0. Here we don't have a sigma, we have a 1. And how do we do it? So this one, the blue one, is the unit normal. If we multiply this unit normal distribution with the standard deviation sigma, how will that look like? What will be changed? So assume if, let's say, maybe I use a different color to be the same. So the blue one, this is a unit normal. Okay, this is a unit normal. And now if I say the sigma is 2, and then this is 1, okay? Then first, if I multiply the unit normal with 2, it will become like wider, okay? Standard deviation here first, 1. If I multiply, then the standard deviation will be changed to 2. Okay, good. Recall here, the center, this is 0. The center here is 0, right? If I plus 1 from this one, then what will be changed? So the entire distribution will be shifted right-handwards so that this center will become 1, okay? So here is 1, here's 2 as well. So now this new shape, this is a new shape, this is a new shape. The new shape has a mean of 0, has a mean of 1, and has a standard deviation of 2. So what is that? That is basically this, right? Normal distribution with a mean of 1 and a standard deviation of 2. So here, what I illustrated is to show you how to reparameterize or rephrase theta using the unit normal distribution, okay? Unit normal, first multiply that with the standard deviation, then plus the mean. So this is the paraphrase or reparameterization of the theta parameter instead of using this original format of quantification. And graphically, it's the same as I said. So the blue one is the unit normal. First, change the width, so it becomes wider or narrower, depends on the value of sigma, and then shift that on the x-axis to maybe travel to the right or to the left, depends on the sign of the mu parameter. So in this case, sigma is a little bit wider and the mu is positive, then it becomes centered around 10 and some standard deviation, okay? Any questions up to this point? The nails funnel is not important, but this slide is important because this explains the central idea of reparameterization. It's actually pretty straightforward. We know normal distribution, we know unit normal distribution, and we paraphrase it. We use the unit normal as the simpler word and reparameterize, paraphrase the theta in relation to the unit normal, with here the sigma, with here the mu. Okay. Good questions. First one, is it like a reverse standardization? Yes, I think so. Yeah. So if you do standardization, if you say we have x variable, we want to standardize the x variable. How do we do it? So we say, well, I have x, I minus the mean of x, and then divided by the standard deviation of x. Okay, this is normalize everything. If you do look at questionnaire data, if you want to say, hey, I want to normalize our response items, how we do it, this is to normalize. This is not x normal. This is x normalized. Well, x normalized, good. But if now I want to get back to the original x, how do we do it? Well, the x normalized will be multiplied with the sigma plus then the mu. Yeah, right? This then is that one. Same. Yeah, that makes sense. So you could imagine this is an application of the reverse normalization. We don't want to get the normalized. We want to have the raw space. And then we do this reverse calculation. Yeah, good point. Second question, how do you decide which normal distribution one need, the blue? I don't decide because I will always use a unit normal, 0, 1, always.
I'm sorry, because you said if we take -1, it goes on the left side. So I thought maybe there are different. What did you mean by that then?
By negative?
You said that like when we multiplicate with this blue ones, then it goes to the right, but if or to the left, depending which sign it has. So I thought maybe I can decide what I want. So I didn't understand it then.
No, not quite. So here, this blue one, the theta tilde, this thing, this is a unit normal, right? Unit normal like this. If this sigma is above 1, so then the shape will become wider. If the sigma is smaller than 1, and then this shape will become like much narrower, okay? In these two examples. So this changes the width, how wide that is, the sigma parameter. This is 1. And for the second, the mu changes the location on the x-axis. So this is normal. If the mu is positive, then the normal will be changed to the right-hand side, 0, 1, for example. And if this mu is negative, -1, for example, and then this will be shifted to the left-hand side. This is -1. So there are two effects in total. This changes how wide that is, and then the mu changes how far away that is relative to 0.
Now I got it. So this blue with tilde, it's always the same. It will be always 0, 1 and only. Yes. Okay, now I get it. Thank you very much.
Yeah, sure. Thank you. There's a third question, just for clarification. We reparameterize just for a better computational performance. Yes. So if you see, there will be two versions of the implementation of the nails funnel. One with the reparameterization, the other one without the reparameterization. And you will see how they sample this, how well they sample it, or how poorly they sample it. You will see the difference. The model is always the nails funnel. Reparameterization doesn't change the model per se. It changes how the sampler will sample from the space. And that means the performance will be different according to how we sample from it. Any more questions, comments? Okay, good. Yeah, good. And now the next question is, if you are curious about reparameterization is great, and we have the nails funnel example. So how can we reparameterize the nails funnel example using reparameterization? Okay, so how to do that? The original one is like this: y is normal 0, 3. So recall that, well, we have like unit normal, normal 0, 1. How to reparameterize this? There are 2 parameters always for the normal. This is 0, this is 3. This is 0 means we don't have a mu parameter. The mu equals 0, so we don't have to worry about that. We have a 3 for the standard deviation. So what we do is we will multiply the unit normal with a 3 so that we could reparameterize the y variable. For the x, same. We have a 0 here. That means we don't have to worry about the mu because that equals to 0. We have a unit normal. And as you could tell already, as you could expect, we will multiply the unit normal with e to the power y over 2. So this is the approach to reparameterize the nails funnel to implement. And then to code it up in the standard language, how to do it? Well, take a look here. So we have 3 multiplied with y underscore rho. We have e to the power y over 2 multiplied with x underscore rho. So here then, what is that? What is that? That is unit normal, right? Unit normal, unit normal. And then all the others, like this, stay more or less the same. Does that make sense? So in essence, in the model block, we are writing simpler distribution. Unit normal, unit normal. Simpler distribution is what Stan likes, is also what human likes. Simple language, simpler language to describe the same thing. That's why we are using more complicated language. We are not writing a sophisticated newspaper for New York Times. We are just writing some daily conversations. We prefer simpler language. So in the model block, normal, unit normal distribution. But again, recall, we are not interested in the unit normal distribution per se. We're interested in something else. And then this something else, x and y, they are paraphrased in relation to the simpler language. So unit normal multiplied with 3 is the original y. Unit normal multiplied with this expy over 2 is the original x. Okay? But for the sampler, in this particular case, the MCMC will sample directly from these 2 units, from these 2 distributions which are not unit. Conversely, in this example, the MCMC sampler will sample from 2 unit distributions, unit normal distributions. Unit normal is something that we know, and the MCMC sampler loves the unit normal. So in this second case, you could imagine already the MCMC sampler will perform much better than the original version. Good. There's a comment, and also feel free to ask other questions. So the comment is, just a thought, why not to have only one raw parameter if it is the same, because we have an fx? You mean here we use the same?
Yeah, I meant in the model, it's written y row and x row, it's the same, normal 0, 1. And I thought, like, why do we need two different? And the second fast thought was maybe because we have 9x parameter, but why, because we multiplicate by this parameter.
Yeah, this is a good question. I never thought about that, honestly. So you mean this is sampled from unit normal? This one is also sampled from unit normal. Why we just say something, say, okay, just raw, right? Raw sample from that, raw sample from that. Yeah, that's what
exactly.
I mean. Yeah, that's could work, I think, could work. Let me explain to you so how this works. So to have this one, let's say from the parameters block, we can say this is a vector with 10 elements, and we call it raw. Okay, good. And then this line will be y equals 3 multiply raw, but we pre-assume that row, the first element of row, it will correspond to the y variable, and then the x will be like the e to the power thing multiply with row, okay, 2 to 10. This is how to do that. If we want to say here, hey, here we have a row variable and that follows unit normal, this is how that works. But this lacks the clear association. Say we have a y unit normal for y, x unit normal for x. We have to know the first one is for y and the second to the 10th is for x. So the clear correspondence is lacking if we are doing this way. It's possible. There will be no change in terms of results. Only like how you understand yourself and how your future self after half a year understand your previous coding, and then you forget what is x, what is y. Right? That makes sense?
Yes, thank you.
Yeah. And practically, I wouldn't really recommend doing that. It's not so ideal. Yeah, I will just do this. Okay, good. There's another question, and it says, but wouldn't then be raw just the same value twice for each time we sample? I'm not sure when did you ask that question. So if we say vector of 10, then we have a raw parameter. That 10, all the 10 row variables, each 10 elements inside that vector, they will be sampled independently from the unit normal. So it's not the same.
Yeah. I asked that before you explained it. So
yeah, okay, yeah.
Take that back.
Sure, no worries. Yeah, right. Others? Okay, next question. Is reparameterization only useful for normal distribution, or is there also a benefit in other distributions like beta? Yeah, I will show you later. For the beta, there is a specific reparameterization, honestly, and it's not included in the slides. It's possible, but I will show you. Yeah, I'll show you in a minute. Other questions? I'll skip these slides and I will show you something a little bit interesting. So we have this weird nails funnel kind of example, and we are trying to find out the density of the distribution, and we have a direct coding, and we have a paraphrased version of the same coding. So one, this is direct, the other one is reparameterized. And if you recall that there's a metric that we always wonder after the fitting, we say, okay, there's a R height parameter. If this is above 1.1, that is indication to say the model doesn't converge very well. This is indication. We want to look for something like equals to 1, close to 1, okay? And the convergence, what that means. So if you recall from earlier examples, we have the fitted results, and we always have this caterpillar shape of traces. This is called the trace plot. So all of the traces, they mix up. This is indication to say they converge well. And then in this particular case, they converge very well after the reparameterization. And we wonder how it looked like if we do not do reparameterization. You see here the chains. So there are 4 colors for 4 chains, if you recall the idea, MCMC. Orange, this is like purple, a little bit darker purple, somehow also orange. The 4 chains, each of them, they are just basically doing their own thing. So maybe one chain is stacked here for smaller steps. The other chain is going somewhere the above part, some bigger steps. You see here they basically do not agree with each other, and this is called divergence. They have diverging results, which also means we have set up 4 MCMC robots to find out the random space for us. And we sent them away, and then they returned. We collected the 4 of them. And each of the 4 of them, they are speaking about different things. So they're not talking about even the same things. So how we can be reliably tell the shape of the density? No, not possible. So then we can't trust the results. Here, this is a good example of divergence. We don't want it. We want convergence. And there are some other numbers to look at. So remember, we run 4,000 MCMC samples. And this number means the effect number of samples. If we reparameterize or if we optimize our model, so nearly all of the 4,000 samples, they are effective. In the middle, I tell you later. In this case, out of the 4,000 samples, only 18 are valid. So basically, nothing is really valid. So for the time to run it, it doesn't really differ too much. It's all of the 3 versions, they are around 50 seconds. What matters is if you do the calculation, if you say per time unit, how many effective samples can we achieve? So this 1 second, we don't even have half a valid sample or effective sample. For this one, within 1 second, we have around 80 valid samples, okay? This is the rough idea about how well or how poorly they perform relative to one another. So this is really bad. This is very good. Okay, some other questions, I think. One question is about how much time we save with this. You mean the runtime, I think. Yeah, this is a bit tricky. So if you look at the example I give here, just right now, the time, it doesn't change, it doesn't really differ. But per time unit, the number of effect samples is the more important metric to look at. So per time unit, how many effect samples do we have? This one nearly nothing, this one a lot, right? Good, good. There's another one. Can you quickly repeat what makes a sample invalid? Yeah. So maybe the word of valid is a little bit tricky. So maybe let's use the word as used here. They are called effective samples. Let me try to give an example. So let's say we have a 1-dimensional space, and then there's MCMC robot, right? And then it travels here and here, here and here for maybe 1,000 times. Because the nature of the MC algorithm or the MC robot, the robot is always moving from one location to the next, from one location to the next. So what you can imagine is around some neighboring area, they somehow carry the similar information, right? If I say I move from here to here, the information I get from these two locations, they are somehow overlap. And if I have a large step, if I say I move from here to here, and then the overlap is less, okay? Because they're not neighboring areas, they are like far apart. So this is the nature of the MC robots. So if the two samples, they are very close to each other in these two cases, I use a different color. So here and here, okay? There are two samples. By counting, there are two, but they overlap too much, or they overlap somehow to some extent, 20%, for example. Then in this case, they are not effectively two samples. They are one point something, depends on how much they overlap, okay? For example, 1.3, 1.8, something like that. Good. And so if the effective information from the two samples is equal to 1.8, so then the 1.8 will be the effect number of parameters. Even though we have two, but effectively we have 1.8. And in this case, we have 4,000 in total, but effectively we have nearly 4,000. That means good. That means each of the points, the samples, they contribute more or less independently. They don't overlap too much. In this case, out of the 4,000 samples, only 18 are effective. That means there are a lot of dependencies or something that we cannot even explain. So they're not good. We want to have a lot. We want to have as many as we want to have the effective numbers of we want to have the number of the effective parameters as many as possible. So this is what we want. So this number, we want it to be as high as possible. In this case, too low is really not good. This one is pretty good, pretty decent. Okay, and another question is related to this. How can the 2 points overlap? Can we summarize like this? The samples, when using the reparameterized model, are further apart on average, and therefore it is more effective. In a way, you can say that, but I would say if we use reparameterization, it reduces the interdependencies among the parameters so that they contribute more independently to our results. Does it make sense? So the keyword, there are two keywords. One is interdependency, because we are using reparameterization, so they depend on each other less. If they depend on each other less, then that means they contribute more independently to the results. Okay, interdependency and independence, they are the opposite meaning, obviously. And then the Stan language on its own, there's a manual of 300 pages. There's a chapter that explains reparameterization, and I think they also use the word of to reduce the interdependencies among the parameters. Yeah. Good. Does it make sense? Okay. So now what we do? Wait, there's a question now. In a way, I think I will read up again and reprint. Yeah, go ahead. I could send the chapters in the email. the chapter of reparameterization from the STEM manual. There's a question, so it always makes sense to use reparameterizing, or in what cases it is not recommended. You're right, the first case. If you can, always do it. Practically, so let's try to talk about some practical examples. This is not about this. We will use this white space to draw something. So you will have what I want to write, experiment first. And when you have experiments, you have data, right? And after the data, you do a cleaning. So do data cleaning to remove some invalid responses, missing data, outlier, blah, blah, blah. You do some pre-process of the data. And then you have a post-pre-processed data. The post-pre-processed data will be the data set that you will be working on, generate results, and then make figures and then publish it. This is how that works. So one of the analysis is to do model, right? You want to do modeling. So you say, well, we have a model, we have something unknown parameter, we want to find the linking function, likelihood function to explain the data. So this is model, to do modeling, statistical modeling or cognitive modeling if we assume also some cognitive processes. Doesn't matter here. So it doesn't matter cognitive model or statistical model, just a model. We have a model, okay, good. To where to find a model? So where to find a model, that means what the equations are. What are the equations? Maybe a linear regression, like y is axb. I don't know what I do this, well, c plus dx, whatever. This is one model. And then there can be another model like the Risk-Wagner, okay, b alpha pe, okay, whatever, they are the models. The model means you find out how to construct the likelihood and also the linking function, okay? In other words, find out the equation, how the model looks like. If you want to code the model, how you can code it. So here, first, mathematical form, you cannot really fit a model by just writing the equations. That's not working. That doesn't work. You will have to translate everything into a STAN language, okay, STAN language, star.stan file extension. So you will have a STAN version of linear regression. You will have a STAN version of Risk-Wagner, okay? These are the two STAN models. So what we have been working on so far is we direct code from the equation to the STAN, from the equation to the STAN, without introducing the idea of reparameterization. But now that you know, you're aware of the idea of reparameterization, if you code the STAN model, what will you do? Will you first have a direct version and then optimize it? No, you will start already with the optimized version, given that you know something called optimization, right? You know it, so then you do, so you know there's a best way, so then you do it, you start with the best way already, rather than you code it from simple and then optimize it. Well, simple means direct translation. That's a good question, I think. Yeah. So long story short, I erase a lot of these things. So we are here, right? We have data pre-processed, good. We have a model you get from a paper, for example. I will always recommend you to feed the model to the data using STAN, because there are other ways to do it, which is not great, because that's why we also talk about STAN. So use STAN as a model fitting tool together with the reparameterization optimization. So always do this. So whenever you write a model, use STAN together with the optimization approaches that we talked about so far. And then later results, then as usual, I think. Good. Any other questions? Yeah, good. I haven't explained the middle part. What is that? What is the adjusted direct model? That is still a direct model. So here this is direct. Here this is adjusted direct. What was adjusted? What was adjusted? So this one, we will go back a little bit. So recall the idea, we have the MC robots. We have 4 MC independent robots, right? Each of them, we run 2,000 samples. Among them, 1,000, they are the warm up, okay? So in the end, we will have 4 multiply 2,000, 2K minus 1K. Then we have 4,000, yeah? Samples, good. This is default. And usually the default works pretty well. And if sometimes, if we run it, there's a warning message to say, hey, there's a problem. So how can we solve the problem? Usually, the most straightforward way is to increase the samples. Now we have 4,000, maybe how about 8,000? To achieve 8,000, there are 2 ways. One is to increase the number of chains, number of MC samplers, maybe from 4 to 8. Well, this is not really good because the chain is short and equally short. If that doesn't work well for 4 chains, it really wouldn't work well most of the time for 8 chains. So what you do is to increase the number of samples. So instead of 2,000 minus 1,000, we could do to double it, right? So we have 4,000 minus 2,000 and 4 chains still, then in total we have 8,000 samples. And the samples is also called iterations. So how many iterations we run, how many samples we run. And here, this is that. To adjust the model, the first way is always to increase the samples from 4 to 8. Okay, 1,000. Good. And there's another way to make our sampling a little bit more fine-graded. So what is that? So here we have the original MC robots. If I'm here, the current location, and I propose to the next, and the next is higher than the current, I do the ratio is above 1, so then I will go there for sure. But if I have a current location here, and I propose the next to be here, so then again, we calculate the ratio. So here, maybe let's say 3, here 6, like 3 over 6 is 0.5. So I will have a 0.5 probability to move from the top, relatively higher position to the lower position, okay? So that means what? That means half of the chance I stay here. The other half, I go somewhere lower. Good. But to have a fine-graded model, to have fine-graded sampling. So fine-grade, what that means? Fine-grade means to visit these places as many as possible. Maybe even though they have lower density, you still want to go there. So to increase the delta means to increase this number from 0.5 to something. Even though 3 over 6 is 0.5, but you want to adjust this one so that it's a little bit larger than 0.5, maybe 0.6. So even though it is also not quite high, but the probability to go to the lower position is higher than the default. So this is the increased delta. In other words, go back to the larger picture. You have a current position. You make a proposal. The proposal means you go to the next. And then depends on the next, if that is higher or lower than your current, you go there or not go there. You go or either no go. Increased delta means you will increase the probability to accept the proposal of your next move, even though sometimes the proposed position will have a lower density, okay? To increase the chance to accept the proposal to go there. And then this one, step size is step size. So if I go from here to here, then that means large step. If I go from here to here, that means small step size. Fine grid, that means, well, as small as possible. I use small step to find out each small, tiny information so that I can get a more precise information. So decrease the step size. And then there's also something called this one. This is too much to explain. This from Stan algorithm. Usually to increase this is the way to solve it. Increase the tree depth. This is too much. It doesn't matter. So the first three is more important to remember for practical reasons. The first one, to increase the number of samples. Here, to increase the chance to accept your proposals. And here, to decrease your step size, to move as little as possible. If we do all of the three, so we will have really a fine graded sampling schedule, as you could imagine, okay? And then how to do this instead, and if you want to do this, and then this is the place to change all of the parameters. And this one, the table is for information only, but that means the same thing. That means here, let's say from default 2000 sample to 4000 asset. Here the default delta is 0.8, we change it to 0.9, for example. Here step size default 2.0, we can change it to 1.0. This tree depth default 10, we can change it to 20, okay? So those are the Stan internal algorithms. We can change it. And after understanding this part, we can look at the column in the middle. So this is the adjusted direct model. So here I forgot already what I changed, but I think I increased the chain length to 4,000 samples, from 4,000 samples to 8,000 samples. I changed also the depth delta. I decreased the step size. I also increased the tree depth as much as I can. But what I want to illustrate to you is that even though I do the adjustment, you could imagine maybe doing the adjustment will improve something a little bit. Yes, it improved a little bit, but not much. If you look at here, the original location here, the four chains, they are really not so agree with each other. And here they show somehow similarity among the four chains, but still here you see a lot of discrepancies, and here it doesn't go well, right? So this adjustment usually is helpful, but doesn't do much relative to reparameterization. So reparameterization is always the solution to go. So do reparameterization. Sometimes if you think about it, sometimes if you do reparameterization, if that still doesn't work, how you solve it? Well, then you go here. You do a adjusted reparameterized model. That is usually the most complicated. You can imagine, I guess. So we will already reparameterize everything, but again, that might cause problem. If that happens, we do this, okay? Good. Practical advice is if you have a model you haven't yet parameterized or optimized, don't do this first. This really won't help much. Try to first optimize it. Reparameterizing is the first, also vectorizing, also others. If that still causes problem, go here to try to adjust some Stan algorithms, like increase the chain length, increase the acceptance rate of the proposal, or decrease the step size so that each time it moves a little bit smaller. Okay. Good. There's a question, I think. Is it always good idea to scale the warm up with total number of iterations? Yeah, it's recommended, I think. So yeah, okay, let me try to explain a little bit more. So default, we say we have 2,000 samples per chain, and half of it we will do warm up. Warm up is to find out if you recall the purpose of warm up, why Stan needs warm up. The warm up is for Stan the algorithm to try to fine tune some internal optimization for you. But the internal optimization isn't the reparameterization. It's only for the algorithm. Okay. So 1,000 step, half of 2,000 is usually recommended. If we run 4,000, then we need 2,000 to run the warm up. There's another scenario. So some of the models, it might take, if maybe the model is complex, and it might take longer time to for Stan to find out internally the optimization. So in that particular case, what you can do, sometimes I do this. So I have 4,000 samples in total, but I have 3,000 samples, so 3/4 for the internal adaptation or internal optimization. This sometimes help me. And then this is like a practical tip. You can try that. If the model is complex, even though you run longer samples, instead of using half for warming up, you could really use even more, like 3/4 of the samples to do the warm up. And you can do this even more. Sometimes I have a collaborator, and once I said this idea to him, and he was like, okay, I will run for 8,000 and 7,000 out of it. This is for the warm up. And instead, still 1,000 valid samples afterwards, not valid post warm up, 1,000 samples afterwards, 4 chains, so 4,000 samples. Okay. I think up to here, this is a little bit overwhelming today. Let me summarize what we have achieved. So we have a problem. The problem is the model is not optimized in terms of how Stan could sample from it. If the distribution is not unit normal, sometimes it is not great. Stan likes simple languages. So we want to paraphrase or reparameterize our model so that Stan could sample from simpler distributions. Okay, so here they are simpler distributions, or in fact, the simplest distributions for Stan to sample from. And we construct back the variables that we're interested in. We're not interested in the unit normal, but we are interested in here and here. And we construct X and Y in relation to the unit normal by changing the scale, by changing the location of the distribution. Okay, this is the rough idea from today. This is the central idea, honestly, from today. And you might wonder, there's a next problem we haven't solved. So we have alpha parameter. The alpha parameter, it has ranges, right? In between 0 and 1. We haven't solved that part. Then this how to solve this part. This is the next topic. So let's talk about that. But before that, any questions? Maybe I leave you 10 seconds to think about if anything unclear. Okay, good. So then next, how about the bounded parameters? We have a learning rate. Learning rate is in between 0 and 1. The normal distribution doesn't have a limit. So how to solve this? Okay. We know this already. This is unit normal. This is the reparameterized normal distribution. It doesn't have a limit, so it is from negative infinity to positive infinity. Good. Occasionally, we want to have bounded parameters. Well, not actually occasionally. Oftentimes, we want to have bounded parameters, 0, 1, 0, 5, -1 to 0, something like that. So how to do that? We imply a softmax function on top of the normal. So what is softmax function? Softmax function, if you recall, we have, when we were discussing the Riesler-Wagner model, we translated the value difference, value of A minus value of B, we translated the value difference into action probability, the probability of choosing A, okay? The value difference, it has a range of something like this. So it depends on the model, but let's say the range of the value difference is between -5 to 5. And we have a S-shaped curve so that the value difference is translated into the range of 0, 1, okay? If the value difference is 0, value of A is value of B, they're the same, then the action probability is 0.5 here in the middle, 50% chance level. If value of A is quite larger than the value of B, our probability of choosing A is close to 1, because we know the value of A is way larger than value of B. A is a lot better by not choosing A, so then choose A. Good. The concept here, in terms of value calculation, is not so relevant. What I want to show you is here, this S-curve shape. It translates anything that without a range to something in between 0 and 1. So why not we use or apply this idea when we have bounded parameters? Okay, so if in the center here, if in the center, oops, I will change the color. If in the center, in the parentheses here, this part, this is the same as here, same this. If this one is without a limit, but we want to have something that has a limit, then what we do is we will apply the softmax so that the resulting parameter, this theta, it will be between 0 and 1. Okay, it will be between 0 and 1. Does that make sense? And you might wonder one thing, so what is this? Why that is called probit? This minus thing, minus 1 thing, what is that? This is a terminology. So let's go back quite to maybe the third lecture of the TEWA one, when we were talking about probability distributions, when we have continuous variables. If we have a normal distribution, we have the PDF of the normal, like standard bell shape, symmetrical, great. Associatedly, there is something called a CDF, a cumulative density function. So the cumulative density function is like accumulating the area under the curve. This looks so ugly. This is like accumulating the area under the curve from negative infinity to positive infinity. Right? There's 0, this is 1. This CDF of a normal distribution is this. This is a terminology thing. So if you look at here, this footnote, so this inverse probit, this -1 means reverse. The reverse probit is the normal cumulative distribution function, so the norm CDF, okay? It has roughly the same shape of the softmax. Recall that when we were calculating the value difference, we used the softmax. They are nearly the same, but there's a slight difference, which is not important for the course. If you're interested, you can use Google Wikipedia to find out the difference between the softmax and the inverse probit. There is a tiny difference. Doesn't matter here. Both of them, they translate x, which doesn't have a range, to a range 0, 1. Okay. And in the standard terminology, this inverse probit is called phi most of the time. If let's say there is x doesn't have a range from minus infinity to positive infinity. If we apply phi using x as the input argument, we will get a bounded x parameter. So phi of if x doesn't have a range, then phi of x will be between 0 and 1. And then this one is what we wanted in the beginning. Okay? Does that make sense? If I'm talking something too obvious. Maybe not. Good, good. Perfect. I was just looking at the time. I should stop more or less in 2 or 3 minutes. Cool. Okay, great. So when we have this, everything is solved. We have then bounded parameters, which is what we want. And next question. So the theta parameter now, it is in between 0 and 1. What if we want to have something between 0 and 5? What if I want to have something between 0 and 10? Well, this is easy because if we have phi of x is in between 0 and 1, if we multiply that simply with 5, then the entire term will be between 0 and 5. If we multiply a 10 here, then it will become from 0 to 10. Easy. Okay, this is easy. That means the parameterization can be generalized according to this table here. So this table is my favorite table. If somebody asks me, hey, how to do reparameterization, I give them this table. So look at it, try to find out. And here it has answer to everything. The first line is without limit. This one is always unit normal, okay? Recall this is always unit normal, like indicated here. The first line is to reparameterize a normally distributed theta. This line is to have a bounded parameter. So here from 0 to n, multiply with n, this is the phi x, this is phi x part. Good. And if I say, well, I do not want to have my lower limit to be 0, I want to have two arbitrary limits, m and n, lowest m, highest n. Is it possible? Yes, we could still use the probit like this, phi x, and then multiply with n minus m plus m. In this case, like a numerical trick, so that we will have the parameters between m and n. Great. So let's say, if this is not so obvious, I can give an example. If let's say m is, if I want to have a parameter to be between -2 and 2, so recall phi x is 0, 1, right? Is 0, 1. And first, calculate the distance between the two ends. So 2 minus -2 is 4. Okay, then 4 multiply phi x. 4 multiply phi x is in between 0 and 4. But I want to have -2 to 2. How to do it? Well, minus that by 2. So everything will be between -2 and +2. So this is how that works. And last example. So occasionally I do want to have a lower limit, but I do not want to have an upper limit. So let's say I have something like a positive infinity. As long as it's positive, I'm happy. As long as they are positive. Okay, good. So how to do that? There is also a way to do it. So here we could use simply the exponential function. So you recall exponential function if this is x, this is y, but y equals e to the power of x, we will have something like this, right? This is something we learned from high school, I guess. So the curve is above 0 always. This is 0. the curve never go across this line. No, never. It approaches negative infinity, but this doesn't matter. So all those values on the curve, they are positive. So here we are using an exponential function to reparameterize a positive parameter. Okay. So look again, we have unlimited parameter, bounded parameter, and a one-side bounded parameter. We have these four cases to reparameterize theta. And you could imagine, what else do you need? There's nothing you need. These four cases really covers all the situations in Moodle. No bounded, no bounds, no limits, with limit, one limit, right? One limit. There's nothing you need. Nothing else you need. If you say you want to have a negative infinity to 0, how that works? Well, easy, just minus. Then this becomes the negative one, right? So here, the exponential, then if we say minus, then it becomes this. Then we have the minus values, negative values. Good. Does that make sense? Still? Good. This one I'll do it after the break. Yeah, just up to here. If no more questions, so then let's have a break. Let's be back at 5 o'clock if you have no more questions.